All right, in the last video, we kind of talked about how some of the questions that were asked in the empirical rule section can be answered without using the empirical rule. Maybe you could argue more efficiently answered by using calculator functions. Here we go. There's two calculator functions. In the previous video, I only showed you one of them, the normal CDF function. Turns out, depending on the question that's asked and the information that's given, sometimes you won't use the normal CDF function. You'll instead use the inverse norm function. So, wait, you're telling me there's another function and I have to figure out when to use it? Yeah, but it's not that bad. Let me give you an example. So suppose I have an exam or I have a test where I know that scores on this test are normally distributed. So there's that assumption of normality that we have in every single one of these problems. Normally distributed, I can't write and talk at the same time apparently, with a mean of, I don't know, 70, sure, and a standard deviation of 10. All right, so I give you all this information. You're like, oh, it's normally distributed. Okay, I can kind of draw this picture and draw this symmetric bell-shaped curve just like we've been doing. Good enough. Oh, and the mean is 70, so I could throw 70 in the middle. And then if I wanted to, I could count up and down by 10, so like 80, 90, 100, 60, 50, 40. Although you'll see I'm not going to do that on this example just yet, and I'll explain why in just a minute. Now I want to ask a question here. So here's our first question. If I only want 15% of students, that seems mean. I probably should have made it lower than that, but whatever, to fail this exam, what score should be the pass-fail cutoff? So already you might notice that this question is pretty different, just kind of fundamentally different from the ones we asked in the past. And the ones we asked in the past, there were essentially two different types of questions, and they both were ways to ask you for the area underneath the curve. So either I said what percentage of the population falls within these bounds, or I said what is the probability that one randomly selected observation would fall in between these bounds, and then I gave you the bounds. In this problem, I'm not giving you the bounds. Right? If you read this question really carefully, I'm asking you for the cutoff. I'm telling you that I want there to be some number down here. So not a percentage of people, not a percentage of nights, nothing like that. I want a cutoff, a score, a test score, something that will go down here on the x-axis that is so far over to the left that the area left of it is only 15%. What I'm saying is this question is asking you to find the number that goes right here. I don't know, x maybe? Find this number. You don't know this number. Find this number so that the area to the left of it is only 15%. It's backwards, right? In all the other problems from the previous video, you were trying to find the area underneath the curve. Maybe it was the area above some point, maybe it was the area below some point, maybe it was the area between 2 points. But you were always given the bound or bounds in question, and you were always asked to find the area. What you'll see is sometimes, like in this question, you're told the area, and you're asked to find the bound. It's backwards. What used to be the answer is now the question. What used to be part of the question is now the answer. So how are you ever going to find this? Well, you could guess and check your way there through normal CDF. Lower bound, negative 9999. Upper bound, I don't know, let's try 50. Center would be 70, and spread would be 10. Here's my standard deviation. I could try that and see what I get. And if I get exactly 15%, cool, I'm right, and I'm done. But I'm probably not going to, right? So I'd have to guess again and adjust my answer. It's not a very efficient way to do this. It would be nice if there was a calculator function built to answer exactly this type of question. And guess what? There is. There's a calculator function that tells you the number down here that corresponds with a given area below that number. It's called the inverse norm calculator function. The inverse norm calculator function, unlike the normal CDF calculator function, only takes on 3 inputs. So I already saw normal CDF in a previous video. Maybe I'll write inverse norm right next to it here. Normal CDF, it wants you to tell it the lower bound, the upper bound, the center, and the spread. It would not make sense to tell inverse norm lower bound, upper bound, center, and spread because you don't know the bounds, right? What inverse norm does is it tells you the bound. So you couldn't possibly tell inverse norm the bound. That's what you want inverse norm to tell you. So the inputs have to be different. So what are the inputs? Well, there's three of them. The first one is always the area to the left of the point you're looking for. And then the second one is the center. And the third one is the spread. And again, in this section, center and spread will always be mu and sigma respectively, but I'm not going to write mu and sigma because later on they won't be mu and sigma. And your calculator says mu and sigma, and that's a big problem with your calculator. It'll make your life really hard in future sections. But right now, it's not a big deal. Inverse norm, area to the left, center, spread. Note that for area to the left, always format area as a decimal, not a percentage. You might have noticed that every time we use normal CDF, when we use normal CDF in this problem, it didn't say 9.12. It said 0.0912. It always gave the answers in terms of decimals. When your calculator is talking about area, it gives it to you as a decimal, not as a percentage. So if I'm going to tell my calculator an area, I can't give it the area as a percentage. I have to give it the area as a decimal. What I'm saying is you're going to use inverse norm, and then the area below the point that you're looking for, the area to the left of this point is 15%, the center is 70, and the spread is 1.5. No, it's not. It's 10. Sorry. It's 1.5 in the last problem. It's 10. Note that I didn't count up and down by tens down here because I don't know where x is until I use the inverse norm function on the calculator. When I'm drawing the picture here at the start, I don't know what x is. Say x ends up being, I don't know, 62. I mean, it's not going to be. That's just a wild guess. But say it ends up being 62. It'd be pretty foolish if I put a 60 right here. That's not a 60. If I put a 60 here and a 50 here and a 40 here, and then I said x is 62. You'd be like, whoa, why is the 62 in between the 50 and the 60? What's wrong with you? I'd be like, well, I didn't know what x was when I drew this picture. So the way you get around that is when you're doing inverse norm questions on your calculator, you don't even have to count up and down by the 10. It's fine. I know that you know that that's the spread because you're showing your work down here. You're saying that you're putting in 10 for the spread, so I know you know what you're doing. Inverse norm, 0.15, 70, 10. How do you do that on your calculator? Well, just like normal CDF, it's under the distribution menu. So you hit second and then variables to get into the distribution menu. And it's the third thing listed here. It's right below normal CDF. It says inverse norm. If you have an old version of the calculator, it doesn't really matter. You hit second and then variables to get into the distribution. It's in the exact same spot, normal CDF. The only difference is instead of being prompted for the three arguments that this function is looking for, you just have to have them memorized. You just have to know that the first argument is always the area to the left, so 0.15, then you hit this comma key. The second argument is always the center, so it's 80. I don't remember what it is. It's 70. It's not 80 in this problem. And then the spread was 10. You hit enter, it spits out the answer. 59.64, I guess if I'm rounding to two decimal places. So this answer is 59. Wow, that was foolish for me to close it because I've already forgotten what it was. 59.64. And then I close it again. I could have done that over here as well. Same thing. It's just now it asks me questions. 0.15, 70, and 10. And what you'll see is first, it puts it into this form so it looks just like it did in the other screen. Then you hit enter, it gives you the exact same answer. 59.64. Wait, so 59.64%? What is 59.64%? Nothing. This is not a percentage here. I'm not finding an area. This is a score on a test where 70 is the average score. 59.64 is where I should set the pass-fail mark if I want 15% of people to get less than that amount to fail this exam. So this answer would be 59.64. That's the inverse norm function on your calculator. Let me give you a couple more examples. Example 2, let's stick with this same problem so I don't have to write up another scenario. I still have a test. I still know that scores are normally distributed with a mean of 70 and a standard deviation of 10. How high do you have to score to be in the top 5%? of all people taking this test. How high do you have to score to be in the top 5%? Again, it's not obvious. I think the hardest thing about using these is recognizing when you have an inverse norm versus a normal CDF question. The nice thing is that I'm breaking this up into 2 videos, and this video is all about inverse norm, so it's got to be an inverse norm question. But what you'll see on the homework, one of the big challenges with the homework, is it doesn't say here's a bunch of normal CDF questions and then here's a bunch of inverse norm questions. You got to be able to read the question and tell what type it is. How are you going to do that? Because they're telling me the area here. How do you know that they're telling you the area? This goes back to the first video that we talked about in this section, where the area underneath the curve has 2 different interpretations. It's either the percentage of all people that fall in that range or the probability that one person falls in that range. So in this question, and it's not obvious, it's not explicit, you have to be really clever to figure these out. In this question, it's saying that there is some score that is so high that the percentage of all people scoring higher than that is only 5%. It's giving you the area. This is that first interpretation of area. So it's saying there's some score. Note, I'm going to put it over on this side. You can label it with an X if you want. You don't have to. I'm putting it on this side because it's got to be a really high score if only 5% are scoring better than that. So right here is 5%. So how do I figure that out? Well, it's an inverse norm question. And you're like, yeah, all right, I got it. Inverse norm, first argument's 5%, and then the center and the spread. No. The reason it's not is when you use the inverse norm function, you got to remember that the first argument that it wants is always the area to the left. Problem, I didn't tell you the area to the left. I told you the area to the right is 5%. The top 5%, that's the area to the right of this score. Well, if 5% is to the right, 95% has got to be the left, right? 100% somewhere. So if 5% is on this side, that's telling you that 95% is on this side. You could restate this question to be, how high do you have to be to score higher than 95% of all people that take this test? Same thing, top 5% or higher than the bottom 95% means the same thing. But importantly, when you're using inverse norm, you have to tell it 95% and then your center and then your spread. So same thing, second then variables, getting to distribution, inverse norm, and then the area below is 0.95. The center is still 70, the spread is still 10. I hit paste and it kicks out this score, 86. Point, if I asked you to round to 2 decimal places, 0.45. So the point here is that inverse norm, most people find inverse norm more challenging than normal CDF for what that's worth. And when you'll see the real challenge is when you have both questions and you don't know which one it is. Like the biggest challenge is telling when is an inverse norm question and when is a normal CDF question. And my big piece of advice there is you use normal CDF anytime you're trying to find the area underneath the curve. That's when you use normal CDF. So when do you use normal inverse norm? Use it, and by it I mean this thing, when you are told some area under the curve. Because ideally at this point in the class, you're kind of getting to the point where you can read a question and recognize what it has to do with the area underneath the curve. And again, I don't mean to like beat a dead horse. This is probably getting annoying for a lot of you, but refer back to this. 2 interpretations of the area below a curve are these 2 guys. And being rock solid with these 2 will help you understand what's being given to you in these problems. And if you understand what's given to you in these problems, it'll help you figure out whether you should be using normal CDF, which is the one in green, or inverse norm, the one in this video in red. One more example here of inverse norm. It started out where I gave you the area to the left. That's kind of best case scenario. Then, to be kind of a jerk, I gave you the area to the right. And you had to be clever and recognize that, oh, if the area to the right is 5%, the area to the left is 95%. I want to make it even worse. The middle, 80% of test scores fall between which 2 values? This feels like just some contrived question that a teacher would ask just to try to give you a hard question. It's not. It's applicable to what we're doing later in the class. So it's kind of strange to ask it right now. It sort of doesn't feel like a natural extension of these questions that we see. But it ends up being more relevant than a lot of this other stuff for what we're doing in the second half of this class. So that's why I ask you them now. Here's my normal distribution. I still know that 70 is in the middle. What they're asking for are 2 test scores. And these 2 test scores are supposed to separate the middle 80% of observations from all of the rest of them. So there's some number over here and some number kind of symmetric over on this side that captures the middle 80%. What I'm saying is this area in the middle in here, shaded in green, is 80%. And you're supposed to give me 2 answers. You're supposed to give me the answer that goes over here and the answer that goes over here. How are you going to figure those out? Well, you're told the area. So it's not a normal CDF question. It's normal CDF when you're trying to find the area. You're told the area is definitely an inverse norm question. You have to use it twice, though. First over here, I'll use inverse norm. Inverse norm, first argument of my calculator, it wants the area below this point that I'm looking for, below x. How much area is below x? It's not obvious. It's not obvious at all. Right? 80%? No. 80% is not below, meaning to the left of this point. You're like, oh, right, it's 20%. No. 80% is shaded in here. That means 20% is not shaded. Because it's the middle 80%, that 20% is equally split on the left side and on the right side. So what's going on is there's 10% over on this side and 10% over on this side. So when I use inverse norm to find x here, I'm going to tell it the area below the point that I'm looking for is 10%, or formatted as a decimal, 0.1. The standard is still 70, and the spread is still 10. Type that into your calculator. Inverse norm, 0.1, 70, 10. Hit enter, and it's going to spit out this number. 57 point, if I rounded 2 decimal places, 0.18. So you can write x equals or just equals, whatever. And you're like, so that's my answer? Nah. The question said, between which 2 values? Between this value and this value over here, I still need to find this value. How are you going to find this value? Well, it probably won't surprise you to hear that's an inverse norm question. But where the crux of the problem is figuring out how much area is to the left of this point. Probably think 80%, it's not 80%. Maybe you're thinking 90%, it is 90%. Whoa. Why 90%? Well, here's one argument. 10% is to the right of it, so therefore 90% is to the left of it. You don't like that? All right, here's another argument. 80% gets me this far, but then I need another 10% to get me all the way to the left. One of those 2 arguments, maybe, will convince you that this should be 0.9. And so I'm going to use inverse norm, second and then variables. Inverse norm, 0.9 is the area to the left, 70 and 10. And then I'll hit enter. In this case, I'm getting 82.82, I guess? Sure. Those would be my 2 answers. 2 more little things I want to show you, and then we can call this video good. The first thing I want to show you is some of you might have a calculator even more up to date than this one that I'm showing you. Not very many, but a few of you might have one. Some of you, when you go into the inverse norm function on your calculator, it might ask you for the area, and then it might also ask, is that the area to the left, to the right, or in the middle? If you have that, good for you. You can make these questions easier. Right? For if you have that, if you have an option that says left, right, or center or something like that, instead of figuring out that the area to the left of x here is 95%, you could just tell it 5%, 0.05, and then select that that's the area to the right. Some of your calculators are more flexible and they let you give the area to the left, to the right, or an example like this in the center. But most of you don't. For most of you, when it asks for area, it means the area to the left of the point that you're looking for. So just in case any of you have that fancy type, I wanted to talk about that briefly. One other question. If you can answer this question, you have a solid understanding of everything we've done in this video. Without any context at all, no English, I'm not going to give you any problem. If I took my calculator and I said normal CDF 57.18, 82.82, 70, 10, what would you expect to come out of it? If you can answer that question, that is really impressive. It's probably more than you should be able to do at this point. This would really connect together the last 2 videos. Because note, everything in this video has been inverse norm. I'm doing normal CDF. I'm jumping back to the previous video. So what is this asking? This is asking the calculator how much area, because normal CDF always finds the area, is there under a normal curve in between 57.18, note that's what we got here, 82.82, that's what we got here, if the center is 70 and the spread is 10. What we should get is a number very close to 80%. You'll see it won't be exactly 80%. And that's because I rounded these two numbers. This wasn't really 57.18. It was like 57.1815, something like that. But if I hadn't rounded these, this would have been exactly 80%. Don't believe me? Let me show you. Quit out of this one. Whoops, quit out of this. Second, variables, normal CDF. For my lower bound, I'll put in 57.18. For my upper bound, I'll put 82.82. For my center, I'll put 70. And for my spread, I'll put 10. When I go down and hit paste, what you'll see is the answer is really close to 80%, 80.02%. Slightly off because I rounded these answers, right? 57.18448433. I call it 57.18. If you can understand why this is about 80%, then you're kind of seeing the connection between inverse norm and normal CDF. You have a really good handle on this stuff because this stuff is challenging, the difference between inverse norm and normal CDF. My advice to you is to start the homework on inverse norm and normal CDF with just this knowledge and read through the problems and see if you can tell which ones are inverse norm and normal CDF. And if you could tell, then great. And if you can't tell, I have a lot more resources of stuff you can look up for telling the difference between normal CDF and inverse norm. But if you're getting the hang of it already, don't waste your time watching more videos on this stuff. But if you need more help, I have lots more videos on these, lots of quizzes. Look for 3.1 calculator functions.